Cool. The recording button's moving, so yeah, right. So today's tech talk is about OpenShift virtualization, also called CNV. So what is CNV? Well, container-native virtualization is a Kubernetes technology that allows the execution of virtual machines in containers. That sounds absolutely insane. Absolutely insane. The whole point of containers is that you get much more density in terms of the stuff you can run, and they are designed to be disposable. You run up a container, it dies, it gets reorchestrated by Kubernetes, all those wonderful things. So why on earth would you want to run virtualization in a container? Well, from an OpenShift perspective, it makes complete sense. You know, OpenShift offers a level of security above and beyond Kubernetes in terms of the way we control access to the resources and the way we control actual access to the applications themselves, control the ingress, control the SDN, and all those kind of things. And being able to execute virtual machines as de facto containers means that you get the advantages of security, you get the advantages of the RBAC, you get the advantages of the orchestration plane, singular from an OpenShift perspective. Now, before we dive into the tech itself, I've got to admit, I love CNV and I hate CNV. And the reason I love CNV is that it's a beautifully elegant technology, as is Kubernetes. It's a fantastic technology. And once it clicks as to what it's doing under the covers, it'll blow your mind. It really is a clever piece of tech. But the reason I hate it is that it removes the compelling need to modernize the applications. And I'll explain that. Let's say you've got a suite of virtual machines running your apps, and it would take some effort to reorchestrate them and re-engineer them into a container. Now you can just lift and shift those VMs as is into OpenShift. And they're executed as containers themselves. They come under the same security controls. They come under the same namespace controls, same ingress controls. There's no compelling need to modernize the application. And so it always amuses me slightly when I'm talking to customers, because they look at it and they say, oh, brilliant, I can just move my entire estate as is under OpenShift. And you can, but you don't get the advantages of containers, of containerizing the applications themselves. But there are use cases for it. So why on earth would you want CNV? The primary strengths of containers are massive reduction in footprint due to layer sharing and run anywhere, fail anywhere. The reason I'm reading this fast is I want to get to the tech, so bear with me on this. VMs are persistent entities and they don't take to destruction and recreation very well. They don't like it. But what about modernization the easy way, without having to instantly re-engineer the application? Be able to lift and shift your application with its services, with its web services, with its microservices in a virtual machine, run it in OpenShift and expose those services as OpenShift services. And that makes it very, very nice to be able to lift and shift an existing virtual machine into a next generation orchestration system and use it. And what about legacy workloads that don't lend themselves to containerization? I'll give you good examples of these. We've never been able to touch the Windows market. You know, from a Linux perspective, from a Red Hat perspective, we've never been able to get at the Windows suite. With the virtualization technology, we're partnering with Microsoft on something called the SVVP. And the SVVP program basically allows Microsoft to provide support on a containerized version of their operating system as if it was the operating system. So if you've got Windows Server 2012, 2016, or 2019, you can actually run that as a virtual machine under OpenShift, and Microsoft will provide support across it as if it's a standard operating system. And that's huge. That's a real indication from Microsoft that they believe in this tech. And what about applications that need specific operating system settings that don't lend themselves to containerization? Additional drivers, additional network interface cards, things like that, things that are a pain in the arse to do, although you can do it with Multis on OpenShift. Well, what about a single point of control, both for orchestration? I'll give a good example of this. I was talking to one customer, and they'd containerized their backend system. So they produced a number of microservices that they were operating through containers, and they had a front end that was a .NET front end that was running on Windows VMs. And they had to change the schema of the database that influenced both the microservices and the front end system itself. And they could not orchestrate a single downtime to be able to pull the microservices down, replace the schema, pull the actual virtual machines down, and get them to come up at the same point, because they were being orchestrated by two different systems. Now, if those virtual machines had been actually running as containers as part of CNV, it's just a simple redeployment. It's a simple re-execution of the deployment of the virtual machine. And you can automate that with things like Tecton. to make a rollout of a new version of a multi-tier application, where part of the applications are in VMs and part of the applications are actually in microservices, as a single point control, because everything is now orchestrated by a single platform. And what about the workloads that cannot, for cost or technical reasons, be modernized? Now, we all know about these. They're the boxes that sit in the corner of the room with the Windows, good old-fashioned .NET applications on them that can't be modernized, that are too much effort to be modernized. If they can be virtualized, they can be executed as a container on OpenShift. But enough with the concept. Let's talk the tech side of it. So the good stuff on CMV, how it works. It took me a long time to work out this. And I must admit, I had to have a lot of conversations with the engineers around CMV to work out what it was doing. But once it clicked, it makes perfect sense. And it's a really beautiful technology. The concepts behind it are extremely and beautifully simple. The virtual machines themselves are persisted as persisted volumes. So the file structure for a virtual machine is expressed as a PVC. So when you bring a virtual machine into the system, it's written into a PVC or a data volume. And then what we do from an OpenShift perspective is we offer what's called launcher containers. And these launcher containers, if you can imagine them, are simple buckets that have the actual API for running the virtual machines. And that API talks to the kernel on the node on which they run. So those actual containers are spun up on a node. The virtual machine is expressed into it as a persisted volume, and then it's executed as a virtual machine directly on the kernel. And that's a very, very important thing to realize, is because we're doing that, you've got the control of the mechanism of the virtual machine through the container itself. But the actual API is the same API that's used by Rev. It's the same API that's used by libvirt. It's QEMU. Under the covers, that container is just a hook into the virtualization system. And the virtual machine is expressed as a persisted volume into that container. And once that clicks, you realize how cool this is. It's not running a virtual machine in a container. The container is the throughput mechanism to control the virtualization on the node. So you don't have a performance hit. And that's very important, because one of the things I first worried about when I was looking at this was what kind of performance hit there would be with running a virtual machine actually in a container. And there isn't one. It runs at the same speed as Rev. Now, you do have to tailor your system. You do have to have RHCOS, Red Hat Core OS nodes. This isn't supported on RHEL 7 or RHEL 8 worker nodes, which I found to my pain when I was working on POC with IBM. When executed as a container on a node that has virt enabled, these containers act as a self-contained hypervisor. So you can imagine each of these containers is a hypervisor in and of itself. It controls the starting of the virtual machine. It controls the controls of the memory of the machine, the aspect of the machine. If the virtual machine has to be moved or migrated, that's done by the QEMU via the controls within the container. And the VM is a file system expressed into one of those VM launcher pods. And that's the simplicity of it. The launcher pods themselves contain the mechanisms for running the virtual machine. The virtual machines are expressed as a persisted volume into the system. So installing CMV on OCP 4.6, what we've done with CMV, which is actually called OpenShift Virtualization, I've got to stop calling it CMV because I've been told off by the engineers. OpenShift Virtualization, it's available as an operator within the Operator Hub. So what we've done is we've wrapped the actual creation of the 2 custom resource you need into an operator. And that operator is actually downloadable and installable on OpenShift 4.4 Plus. It's free, and I know the salespeople hate me saying that, but it comes with the subscription. So when you buy a subscription for OpenShift, you've got virtualization there already. When you install the OpenShift virtualization operator, it installs 2 custom resources. Now, I'll give you a very, very quick introduction to custom resources for people that don't understand what those things are. The whole of OpenShift 4 is built around operators. Operators are a fantastic concept that allows you to extend the object model of Kubernetes without extending the base Kubernetes itself. And I'll explain that very, very simply. Kubernetes is actually a set of while true loops. That's all it is. It's a set of controllers, and each of these controllers is a while true loop. Each of these while true loops owns a single type of object. And Kubernetes has a certain number of objects you can play with, namespaces, pods, services, etc. These controllers sit in a while true loop waiting for requests to create a new instance of that object or a change to the state of the existing object. And what the operator framework allows you to do is to install applications onto Kubernetes in pods that become custom controllers. So you can add additional objects to your Kubernetes object model without changing Kubernetes itself. And that's huge. That's why OpenShift 4 is so beautiful, because OpenShift 4 itself is a set of operators running on top of base Kubernetes. So we have an operator for virtualization. And what that does is it allows you to push, there are two custom resources it provides. One is the creation of the hyperconverged virtualization agent, and the other one is host path provisioning, for when you want to do host path provisioning on the virtual machines themselves. It is incredibly simple to do, and what I'm going to do very, very quickly, because I'm feeling particularly brave, bear with me 1 second. What I will do is I've got a version of OpenShift running here. It wasn't a little bit of a state, but it should be all right. It's a clean version of 4.6. What I'm going to do is very, very quickly show you how easy it is to install the virtualization agent. So you have something called OpenShift Virtualization. It's available through the actual hub itself. I click on install. What that will do is basically add it into a specific namespace on the cluster. And this is the operator, not the virtualization agent itself. So this is the thing that controls the actual installation of the virtualization agent. So what I've done now is I've just chosen OpenShift Virtualization, left everything to default, and hit install. So that's going off and it's installing it. It's creating a namespace called OpenShift CNV, and it's running the operator in it. I'll leave that going. When that's actually finished, I'll come back and I'll show you how easy it is to install the virtualization itself. I've also got some demos of some virtual machines running, which I'll show you as well in a second. Once the hyperconverged custom resource has been instantiated, the cluster will have the appropriate images available for the Virt launcher. So what it does, the operator when it's running, when you install the HCO CR, is it pulls the images required for those launcher images. It also pulls some very cool guest images. I'll explain what they are later when we get to the Windows side of this, because I was pretty impressed by how useful that guest image was with the Windows stuff. So creating virtual machines on OCP 4.6. Once you've got the actual virtualization operator installed, and once you've installed a version of the virtualization agent, there are two basic ways to create a virtual machine on OpenShift 4.6. One is through the opinionated user interface, and I'll show you some examples of that. And the other one's through a command line called virtctl, which gives you a command line access to the virtualization agents themselves. And with the demo, I've actually pre-created two virtual machines in different ways. With the Fedora one, I actually created it from the live image of Fedora. I actually used a URL in the user interface to pull that image across. That image was pulled across by what we call an uploader pod. The uploader pod actually takes an external QEMU image and converts it to that PVC I told you about that's actually used by the virtual machines. With the Windows one, what I did was I downloaded an evaluation image for Windows 10, and I used VirtualBox on my Mac to create a running version of that. I set up my user account, went through all the kind of bump from installing it, setting it up. When I'd done that, I used QEMU-IMG, which is a command line utility, to convert that image from the VirtualBox format to the QEMU format. And then I used the virtctl command to upload that QEMU image directly into a PVC. So I didn't create the virtual machine from the virtctl. I just created the PVC. And then in the interface itself, when I went to create a virtual machine, I could use that pre-existing PVC to spin up a virtual machine. Right, I'm going to go through a couple of use cases on this perspective. Let's go, before we do that, let's go and see if the actual operator is finished. Yeah, so the operator is finished on this cluster here. We're going to look at the operator itself. You'll see it offers two custom resource definitions I can consume. One is the virtualization deployment itself, which is the hyperconverged approach, and the other is host path provisioner for when you want to do virtual machines based on host path, which is when you bolt the virtual machine onto a piece of disk space that's on the actual nodes themselves. That's kind of frowned upon because it means that that virtual machine has to live on that node because the virtual machine is there. We tend to say if you want to run a virtual machine, go down the PVC route. The only thing with the PVC is that you have to have a decent backend system for the storage, but I'll explain about that in a minute. So what I'm going to do here is just basically create an instance of the OpenShift virtualization engine. I'll do this by hitting create. So what that's doing now is it's getting the operator to install all those images I told you about. It's getting it to make sure and check the nodes are prepped for the actual running of virtualization and stuff like that. And what's lovely about this is once that custom resource has been run and that hyper-converged aspect of the OpenShift operators has been put in place, the user interface will change. And the reason for that is that the OpenShift 4 user interface is extensible based on operators. And coming soon, what we're going to allow people to do is write OpenShift user interface components as part of the operator manifest. So you'll be able to add additional screens and additional sort of control mechanisms into OpenShift directly from the operator manifest. Now I'll check it very quickly because it's actually progressing. So I'll see if it's running. If we go to workloads, you see virtualization has already appeared in the workloads. So I can go and look at the virtualization side itself. Not sure what state it's in because the virtualization agent hasn't reported itself as being ready yet. I'll leave that for a second. We'll come back to it in a second because what I want to show you very, very quickly is the steps I went through to create a full Fedora 31 virtual machine. So what I did with this was I used the URL for the Fedora live disk, if people have seen that. It's basically a downloadable image which contains a runnable version of Fedora that gives you two options when you start up. You can either run Fedora or you can install to the hard disk. So I used the OCP create virtual machine wizard, which I'll show you in a second. I gave it the URL for the Fedora live disk, set the resources for medium, because it allows you to choose which resources you're going to apply for that virtual machine. Same with any virtualization management agent. And then what I've done that, OCP imported the live disk image from the URL into a PVC and executed one of those launcher images with that PVC attached. And what, for an example, I mean, I'm feeling brave because the demo gods are usually reasonably happy with me. Let's have a go at it and see what we can do. So we're going to choose new from wizard on a virtual machine. Let's call it Fedora test 1. We'll call it Fedora test 1. Select operating system of Fedora 31. That's just, the reason you do that is that the OpenShift virtualization agent has a number of guest agents that it uses. I'll explain a little bit about that before I carry on. If, for example, you're doing a Windows VM, the Windows VM by default doesn't have something called VirtIO installed. And VirtIO is a driver that allows it to use virtualization for networking and virtualization for storage. So what you have to do is you have to install that driver. Now, to make it easy, what we've done is if you choose Windows 10 or one of the Windows flavors as the operating system, when you install and run the actual virtual machine itself, the system will attach a CD to it. It's a virtual CD. And that CD contains all the installation media for VirtIO, which makes it incredibly easy to just run up a virtual machine, click on the CD in the actual operating system itself and install the VirtIO, which then gives you full access to the network and all those kind of things. But anyway, we'll go with Fedora on this. Boot source. Now, there are 4 different types, and there's a slide later, but I'll preempt myself at this point. With a URL, that will actually go to that URL and pull it down, uncompress the image, and create it as a disk, as a PVC that's expressed into the virtual machine. You can use an existing PVC, and that's what I did with the Windows one, where I uploaded the existing Windows VM using virtctl, and then used an existing PVC to attach that to the back end of the launcher container. You can also use container, and container is basically an interesting one because container allows us to create pre-existing virtual machines. And the reason for that is that, let's say you want to do some tests on a base Fedora and you don't want to be asked with creating the PVC and doing those attachments. You can create an image that has a read-only file system that has that virtual machine in it. And what we're planning to do as part of the OpenShift virtualization is ship it with a number of templates that you can use to just spin up very quickly the virtual machines to do some testing. We don't suggest you use that for long-term virtual machines because the virtual machine image is not in a PVC, so it's not in a write-only and a persisted version of the file system. So any changes you do to that virtual machine will be lost when that virtual machine container goes away. And that virtual machine container could go away because it's been hibernated or it's crashed or the node's gone or something like that. And when it's recreated, it'll be recreated from the state it was when that image was created. So you can do that way. But well, we've done that for testing and to allow people to do things like standing up CD drives and things for virtual machines. And finally, Pixie Boot. And what Pixie Boot allows you to do is create a virtual machine, but create it with additional network cards. So use a Pixie Boot to do a network boot of a virtual machine. There's a technology called Multus, which allows you to express multiple network cards into single containers. Telcos use it a lot. We use it a lot in the OpenShift virtualization to express different network interface cards. By default, when you spin up a virtual machine, it sits on the SDN that's the internal SDN within OpenShift. And I'll show you some examples of that in the demos. So I'm going to do a URL disk. The URL, luckily I've been to the Fedora project a lot, so it's there already. The flavor allows me to pick a sizing. So a medium one is something like 4 gigs of RAM, 2 core, I think, off the top of my head. And you give it a profile, which gives it sort of another sort of flavor around the sizing of the virtual machine itself. Next on the wizard, it gives me the network interfaces. You can add additional network interfaces, but by default, you've got this concept of a masquerade network. What that masquerade does is it wraps the SDN of OpenShift and expresses that into the virtual machine as its network card. And it works exactly the same as every service in OpenShift. So OpenShift itself creates services which are the endpoints by which traffic ingresses into running applications. It's exactly the same with virtual machines. I'll show you this later on in the demo. It'll make more sense there. 2 disks, Cloud Init disk, because it uses Cloud Init to actually start it up, and the root disk itself, which is a 15 gig disk. That should be okay to fit the actual live image on. I'll show you what I did to actually install it afterwards, because this is actually really cool. I'll leave Cloud Init as is. It's going to default to the standard storage class. I won't choose the other one because Ben Holmes is on the call and he doesn't like people using the really cool storage stuff. And I'll hit Start Machine on Creation. And that's done. So what it's doing now is it's running up an importer pod. That importer pod is running up as a pod on the system within the namespace. It's then pulling that image directly from that URL. And that image will be pulled in. It will be decompressed from the original format. It will be then expressed as a file system with the virtual machine in it, and then provided as a PVC into the back end of the virtual machine running in the launcher container, as I described earlier. There's often a little bit of flick while it's setting up the volume itself. If we have a look, I don't think it's got anywhere, so that hasn't actually started yet. Once the volume has been attached and once the pod has been downloaded, because it actually downloads the importer pods the first time you call it. Next time it'll be there when you want to use it first time. Once that pod starts up, the count will start, and that'll be actually it physically downloading. If we go back while it's doing that, so give it some time to catch up. What I did, again, step 4, OCPO imported the live disk image and executed it as a VM. What I then did, first thing I did was I shut the virtual machine down, because the virtual machine comes up and it gives you 2 options, run Fedora or install to hard disk. And what I could have done is I could have added an additional disk when I created the virtual machine, but because my brain isn't working, I forgot about it. I forgot on that example as well. So what I did was I shut the VM down and I added an additional disk, which you can see in the image on the thing here. And what that does is it allows me to create another PV in OpenShift, which is a persisted volume stored externally to the container, and that's expressed into the virtual machine as a disk system. Once I'd added that through the actual controls itself, I restarted the virtual machine, and then when prompted as to whether to run Fedora or install to the hard disk, I chose to install it to the hard disk. And I chose the disk I'd already added, and I installed Fedora to it. Once I'd installed Fedora to it, I shut the virtual machine down, and I changed the boot order of the disks, so it booted from that disk that I just installed Fedora to. And voila, I had a running version of Fedora. We have a quick look and see where we are, see if it's started yet. No, it hasn't started. I'll show you the end product over here. So once it actually is downloaded, once it's actually running, you're given the effectively a virtual machine running within OpenShift. As with all objects within OpenShift, you're provided with a very good user interface, an opinionated user interface that contains information about that object. With the virtual machines, you can see the actual utilization, so the metrics that are being exported, the status. The details are quite useful because that shows you all the information about it. And you can see I actually changed the boot order when I did the installation to the secondary disk. If we go and look at the disks itself, you'll see there's a secondary disk I added, which is a 30 gig disk, again using the VirtIO approach. And that is where the actual Fedora virtual machine has been. I installed Fedora itself. So basically, I used the fixed Fedora live image to create a version of Fedora on an additional PVC. And I say it's just a use case I use to do Fedora. You don't have to do it this way. The virtctl command line gives you the ability to import virtual machines directly from your own desktop, from a URL, and even from VMware. And I think we dropped that from 4.6 because there were some problems with it, but it's coming later. I've got at the end of the slides, I've got a roadmap so I can show you what's coming with that. Started, thank goodness. So it's 32% download. It takes a little bit of a while because it's about 12, 13 odd gig thing. But what it's actually doing is that importer pod is pulling it down and basically uncompressing it and creating the virtual machine image in a PVC. And I can go and look at the pod. No, it's not a very exciting log, but you can see it's actually doing something. What's nice about the user interface, especially the 4.6 user interface, is that it has this concept of being an opinionated user interface. So you can do things like click on the importing information and get direct information as to what that pod is doing. I'll leave that running for a moment. We'll come back to it in a second. Just to show you it actually worked. I want to go on to the next use case and show you what it was doing. So the use case 2 I was doing was exposing a service from within the virtual machine. So I had a Fedora virtual machine running. And what I did was I actually installed, I did a Yum update to make sure it was up to date. I installed Node.js using Yum. I then git cloned an application that I've written for the DevX stuff we've done. And I ran it internally within the virtual machine. So that application is running within the virtual machine and it's sitting on port 8080. Now with a container, what you normally do is a container has the port access, you set up a service, that service is then expressed to a root. With virtual machines, it is identical, and that's what's really sweet about it. So I could run multiple applications in that virtual machine, running on different ports. And then I can create Kubernetes OpenShift services using that bit of YAML on the left-hand side. And the only difference between a service running from a container and a service running from a virtual machine is the selector that actually routes the traffic. So with this, you can see how the selector is vm.kuvert.io/name Fedora test1, which is the name of the virtual machine. And what that does is it ingresses the traffic for this service into that defined port in that virtual machine. And that's incredibly powerful because that service is a native OpenShift object. So when you run, for example, a Node app in OpenShift, you can have a service point. When you run a virtual machine, you can have multiple service points, and they're expressed as services. So you can consume them from other services, and that's where it gets really, really sweet. So what I did was I ran it up on the 8080 port, and I created that service to expose it. And I'll show you it running. If we go back to the actual cluster where I've got the VMs running. So this is the Fedora virtual machine. Let's go back. Okay, thank you. Let's try again on that. It was going too well. All right, we'll leave that for now because that's gone up of its own arse for now. Let's go back to the other one and see what's going with that one. So the Fedora test one we're running on the new cluster, I've just installed the thing. I haven't done the application side. I knew this was going to happen, so this is why I've got a second cluster running. So let's have a look at this one. So this is the Fedora one. If I go to the console, I'll abort the check so we can actually just go and run up. It's going to the standard thing. When this is finished, it'll actually show the Fedora page. And what we'll do is we'll go into the live version of Fedora to show this example. Whilst it's doing that, I shall take this one. This one's come back. So that was, to be honest, that was my mistake for tempting the demo gods. Right, so this is Fedora running the one I was going to show you before I thought it was broken. So I'm going to log onto the system, and you can see you get a standard console for this. This is actually within the user interface itself. So this is Fedora running in a virtual machine. As you can see from what I said, I'm actually running that application on port 8080. Within the machine itself, I can get to that page through the local host. So you can see it's just a standard page. Again, don't take the performance as indicative of the performance of OpenShift virtualization. This is on a nested virtualization system. So this is virtualization, virtualizing a virtual machine. So it's going to be quite slow. So that's running on the local host. What's nice about it is that it's also expressed as a service. And how services work is that those services are endpoints for ingressing traffic. Those services are expressed as a DNS, the individual name to all the applications running in the same namespace. So what I've got here is I've got the Fedora virtual machine running in this namespace. I've also got a little application I've installed from a container. So if we go and look very quickly at the developer side, you'll see I've got an application here. And this application is an image which just contains a shell that can be displayed in a virtual machine. But what I can do is I can actually go into this container. So this container is another application running in the same namespace as the virtual machine. But what I can do is this. Fedora Service 1 is the name of the service I actually created, which links that service point into the virtual machine. And that gives me the page. So I can communicate directly into the virtual machine through that service point using the SDN addressing. What's also nice about it is if I had an application in another namespace on OpenShift and I set up the actual set up the networking to allow me to talk from namespace to namespace, I can access that service using a fully qualified DNS name, something like this. Fedora Service 1. .virttest.svc.cluster.local. What that is basically the service name namespace name.svc.cluster.local, and that's resolvable across the cluster unless you've set up the networking to disallow it. So that allows me to get the page. So you can see what I've done is I've actually run an application in the virtual machine and I can express it externally. Now, if we go back to the use cases. Use case 3, importing a Windows 10 VM. This was my goal. I wanted to try and do this. And again, bear with me because nested virtualization is quite slow. So what I did was I pre-built a Windows 10 installation using the evaluation media using VirtualBox on my Mac. I then converted that virtual machine image from VMDB or VMDK to QCOW2 using QEMU image. So I produced a QEMU QCOW2 version of that image. I then logged onto the OCP4 cluster using the OC command to get the kube config context correctly, because virtctl uses the kube config to talk to the target cluster. I then used the virtctl command line to upload that image into a PVC. So rather than creating a virtual machine, I use virtctl to upload it, as you can see in the output in the command line, into a PVC. And once that had finished, I'll show you very quickly if I go back to the interface. If we go into the namespace and look at storage, we look at the PVCs, you can see I created one called Windows Ooth, which is 40 gig. And that PVC is basically the QEMU image for that Windows 10 machine. I then created a virtual machine directly within the namespace using that PVC as the machine image. So instead of actually pulling a base image from the outside world and then manipulating it, I pre-built that image and brought it in and executed it. And that's the difference. I use virtctl to upload it. And that's what you would do if you were running, for example, in a state of VMware or Rev, where you wanted to lift and shift those images into OpenShift virtualization. Now, going back to the actual use case, so what I did was I used the virtctl CLI to upload the PVC. I then created a virtual machine in the same fashion as Fedora, but this time I chose Windows and used that PVC, the existing PVC option. Now, what was nice about this is that I had to add the disk, because what you do when you actually add that URL or add the PVC, you add it as a disk to your virtual machine. But I had to add it as a SATA disk, not a VirtIO disk, because by default, Windows doesn't have the VirtIO driver. So I added it as a SATA disk, I ran it up, and when I actually ran it up, I looked at the actual virtual machine itself, and OpenShift Virtualization had created a CD with the guest agent on it. And I could click on that guest agent CD and install VirtIO. Once I'd installed that, I had the networking, because that VirtIO driver allows the Windows virtual machine to interact with the software-defined network as a network interface card. And so once I'd done that, the virtual machine, the Windows virtual machine, had network connectivity as well. And I'll show you this. I say again, bear with me, because nested virtualization is not the quickest in the world. So this is the Windows one. In fact, what I'll do, I'll pull it to that external window so we can see it. And you can see it's Windows. And what I've done is I've actually fired up Edge, and I've used the fully qualified domain name of the Fedora service to serve the Node.js page from the Fedora virtual machine into the Windows box. And as far as the Windows box is concerned, that's just another DNS entry. That's just another thing that's being called. And that's the beautiful thing about this, because you can run the virtual machines up in the OpenShift infrastructure itself. And then by expressing it through the services and through the routes, you can just consume it as other services. So if you've got, for example, a legacy application, let's say a microservices running on Windows Server 2012, running on VMware, you could export that, import that as a QCOW2 image, express each of the endpoints as services, and then consume them. And what's nice about that is over time, if you wanted to containerize just one of the services, you could produce a containerized version of the service, run up that container, and then edit the service point to point at your new container. And to the end consumers, there'll be no change, no difference. They're still consuming that endpoint. They're still consuming that root point. Yet you've converted it from running as a service running within a virtual machine to a service running within a container. And that's huge for being able to migrate your existing workloads invisibly to the outside world. But again, this is Windows, so it does have some issues in that because it's running Virt on Virt, it's not the fastest thing in the world. But being able to interact with Windows, and what I also did, so I'll go back to the use case because I'm getting ahead of myself, as I normally do. So that's importing the Windows 10 VM. That's accessing the Fedora service, which I've just shown you, accessing the Fedora service within the Windows VM via the SDN. And I say what's nice and very important about this is that access across the SDN is purely within the cluster. So when you use those service endpoints to talk from one VM to another VM, without having a root, which is the way that OpenShift exposes a service to the outside world, it's all internalized within OpenShift. There's no ingress from the outside world. So you can run these virtual machines within your OpenShift cluster with no access to the outside world. The other lovely thing is, because you're using OpenShift services to interact directly, ingress traffic into those virtual machines, you can use network policies. So network policies are basically an OpenShift extension on top of the networking that allow you to define exactly how traffic gets to services. So for example, you could set a service point into an application within a virtual machine and then set it so it's only visible to other applications running in the same namespace. Or you could whitelist other namespaces to be able to call it. Or you could hide it from the rest of the system. You can make it invisible to the outside world. And then actually have a whitelist for the URLs to allow external entities to access that service, but nothing internalized to do it. I saw that question. Yeah, slides are going to be shared after, along with the recording. So that was use case 4. Use case 5, and this is where it got quite cool, running IIS on Windows 10 virtual machine. So for those who know Windows 10, I had to go into my memory for this because it's been 10 years since I used IIS. I actually installed IIS as part of Windows 10 from the control panel. So I went to the control panel of the virtual machine itself. I set up IIS to be accessible and running. I then did what I did with the Fedora service. I created an external service within OpenShift that pointed at the 80 port within the virtual machine to expose the IIS engine to the outside world, to the actual SDN itself. And if we go back, you can see that what I've got in the virtual machine is I can get to IIS via localhost. I can also get to IIS, I say bear with me because this is not going to be quick. If I do http://windows service 1, I say it's not quick, but what this is doing is it's using the Windows service point rather than the local host. So it's resolving basically the service through the Windows service. And there you are. So I've got IIS through the service name. I can also get at it through the fully qualified domain name because I've expressed it within the SDN. And if we go back very quickly to the Fedora virtual machine, you will see close the tab, that I can actually access IIS through the Windows service service address. So I've got basically backward connectivity from the Fedora virtual machine into the Windows 10 virtual machine. And for me as a developer, that's all I need. You know, I can stand up multiple applications within a virtual machine, and then I can expose individual applications on a service by service basis. But what I can't do with this is access it from the outside world. So that was use case 6. So with use case 6, what I did was I exposed those internal services within the virtual machines to the outside world. And the way this actually works is that OpenShift has a concept of what's called a root. And a root is a fully qualified domain name that allows you to expose a service to the outside world for consumption. So at the moment, those services are actually accessible through the SDN. They're not accessible to the outside world. What I did was I created roots in that namespace. I created both insecure and secure roots, so HTTP and HTTPS, for each of those two service points. And I'll show you, if we go to the actual, and I was lazy, so I didn't set certs on the termination. But if we go to the networking for this namespace and look at the roots, you can see I created 4 roots: Fedora node secure, Windows IIS, and Windows IIS secure. And they are fully qualified domain names that are visible from outside the cluster. So what I can do, for example, if I click on Fedora node, that will take me directly to the application within the virtual machine, but through a qualified domain name that is external to the cluster. And that is the application running on the virtual machine. So you can expose the individual services to the outside world as well. And what's nice about that is you could be running multiple applications on your virtual machine. You can be running 5 applications that are for internal use only, and 1 application that's for external use. And you can control that ingress. So you can have your 5 internal services listing on the service points, on the service names themselves, without roots. And you can have your 6th service with a root, which allows for consumption to the outside world. And this is all really, really useful. And I say this use of OpenShift roots exposes the services to the outside world, but it still abstracts the services. So at some point in the future, let's say you're running IIS on a Windows 10 VM, and you're going to modernize it, and you're going to run the static content on HTTPD in a container. You could run that container, run the source to image process on OpenShift to create an HTTPD, feed it, set it up, run it. And you could then edit the service for the IIS endpoint to then point at the HTTPD container and remove the virtual machine. And the outside world would still be talking to the same root. So you'd still be getting the same information, but it would be being served from an HTTPD container and not from a virtual machine. And that's what I was talking about when I was talking about OpenShift virtualization as basically a modernization technology. So in the old days, when we didn't have this kind of tech, what you'd have to do if you wanted to have a containerized estate was basically go through every application one by one and modernize it and create a containerized version of it, which involves rewriting it, re-engineering it, retesting it, a new form of orchestration, all those kind of things. Now you can shortcut that because you can lift and shift your existing virtual machines directly into OpenShift and then expose them via services and routes so they can be consumed by the next generation applications. And then over time, you can re-engineer them without having any downtime because the minute you've got a re-engineered version, you set up the service point and away you go. OpenShift will reroute that traffic into the new version of it. And that's a very, very powerful way to actually modernize your application suite. And as I said before, for me, the big pitch on this is the ability to lift and shift those Windows virtual machines, to run those Windows workloads as containers. So you have a single orchestration point, a single security point. So you've got the security within the SDN, you've got security within the roots. You've got RBAC controls within OpenShift that allow you to control exactly what objects within OpenShift can consume what other objects. So you can control exactly which objects can consume the services being offered by that virtual machine. So you can lift and shift your existing Windows virtual machines into OpenShift and then orchestrate it from a single point. So this is a very, very quick slide. Again, these slides are going to be available afterwards if you want to have a look at them. The options for creating virtual machines within OCP 4.6 user interface. I won't cover this because I've actually gone over this already, but it's those four: the URL from which creates a disk, the existing PVC, which allows you to basically upload using virtctl an existing image, and then use into a PVC and use that to create a virtual machine. But there's an advantage to that, which is that you can upload a single PVC and then you can create multiple virtual machines from it. Because one of the options in here when you use an existing PVC is to clone that PVC. So I could bring that Windows 10, I'm not going to do it because I haven't got enough disk space, but I could use that Windows 10 PVC I've got existing already to spin off multiple copies of that virtual machine with their own PVC and then have them running different things. And that's one of the lovely things of being able to upload it into a PVC and then clone that PVC. A very quick slide, and this is some new information that's come from the business unit recently, and it's debunking the performance myth, because there's a lot of FUD and there's a lot of uncertainty out there about the performance of virtual machines running in OpenShift, running as containers. And I was worried about this as well, because I was under the impression that before I knew about the launcher containers and the PVCs, I thought it was actually standing up a hypervisor in a container and then loading the virtual machine into it. And you'd have the overhead of having to run the hypervisor in the container and the orchestration system behind it and the virtual machine itself. But now knowing that what the actual launcher containers are doing is giving you a direct throughput into the kernel to run that virtual machine, I know that you don't get any performance hit. So what the business unit has done, what the engineers have done, is they've done some baseline tests with OpenShift virtual machines versus the same virtual machine running on Rev, the Red Hat virtualization. A Red Hat virtualization is just a hypervisor in the management plane. And you can see on the left-hand side, there is some hit on the HPC side. Well, actually, there isn't hit on the HPC side, there's sit on the other side. But they are very, very, very similar in terms of their performance. And it's just going to get better as we optimize it. You'll see in the roadmap, there's a lot of optimization technologies coming down the pipeline for this. And on the actual storage performance for the database side, you're running MS SQL, Postgres, and MariaDB. They're very comparable. In fact, with the Postgres, it's actually up to 5-6% faster running it as a virtual machine using the PVC storage for it. So there isn't a performance overhead of running a virtual machine in OpenShift. You've got to think of OpenShift as another management control plane, a different control plane for the virtual machines themselves. So a very quick look at the 10,000 view roadmap for virtualization going forward. In the near term, we're going to do some improvement on the Windows performance with Hyper-V and enlightenments. It runs okay. I mean, what you're seeing today with the demo is nested virtualization. So you're seeing a virtual machine being virtualized on top of a virtual machine. And that's always going to run very, very slow. I've seen this running on bare metal, courtesy of the IBM chaps, and it runs nicely. It runs very, very, very nicely. So the suggestion is when you do use this, run a bare metal nodes for virtualization. So in the near term, we've got improved golden image template flow, workflow. We've got the ability to create templates. So all that kind of hassle I went through with creating sort of the sizing, the uploading, and all those kind of things, you can build that into what's called a virtual machine template, and then just use that as a sausage machine to generate additional virtual machines. There is some work going on to actually improve that. We are bringing in integration with Tekton. So you'll be able to use Tekton, which is a pipeline tool, to actually do the creation of the virtual machines themselves. You can do it today, because Tekton uses images, and you can actually use that, write those images to do virtctl commands and things like that. We've got IP4, IPv6 dual stack coming. Offline snapshots. We don't have offline snapshots. Sorry, we do have offline snapshots in the near term. Midterm, we've got NUMA coming, out-of-the-box performance enhancements, GPU pass-through for computation, so you'll be able to run HPC workloads in virtual machines using the node targeting to be able to run that container and that virtual machine directly on the nodes that are NUMA aligned, so you get access to the NUMA stuff. Using VMs naturally in developer pipelines, that's the stuff I was talking about with Tecton. In the long term, and this is where it gets a bit mad, in my opinion, we get into the realms of inception. OpenShift nested clusters on top of OpenShift virtualization. So running a virtualized system on OpenShift and the virtual machines you're running on OpenShift are OpenShift clusters. So that's huge. You'll be able to run basically a top-level control cluster, and then within that cluster, you'll be able to run multiple OpenShift clusters as virtual machines being orchestrated by a high-level OpenShift cluster. And that's mad, but pretty impressive. We've got service mesh integration, because currently there's issues with actually using Istio, which is basically Istio uses a service mesh to intercept traffic for ingress. So obviously that's going to cause some issues when you're running against virtual machines. We're going to have integration in the long term with that, align with the OCP stuff. And that's basically it from the roadmap perspective. So that was it in terms of the slides and the demo. Apologies for my voice going and the cluster having a bit of a fiddle. But I'm going to open up now to questions, unless anyone wants to see any other bits and pieces of demonstrations. So feel free to unmute yourself if you want to ask a question. I'll go down the list as well. How different is OSV from KubeVirt? OSV is based on KubeVirt. It's the same technology under the cover. The only real difference is that we have a supported operator, which actually does the pre-installation of all the images, provides the guest images, and we have an opinionated user interface. So with KubeVirt is basically the box of technical Lego for doing the virtualization itself. OpenShift virtualization is the enterprise version with all the tools you need to do it, with the opinionated user interface, with those kind of things. Under the cover, it is KubeVirt, if that makes sense. Will it work on OKD? In theory. You would probably have to craft the images yourself because you don't have access to the launcher images. Because the launcher images, how it works is that because the launcher images are part of the subscription, you can only pull those from the Red Hat registry if you have a subscribed version of OpenShift. But in theory, you can run it on OKD. Worst case scenario, you can run KubeVirt on OKD. So that would do it. How would you license Windows on OpenShift containers? Well, this is the SVVP stuff that we were talking about. The SVVP means that you can use your existing Windows licenses to run a version of Windows as a virtual machine on OpenShift. So same as you get the licensing when you're running it on Rev and running it on VMware, it applies the same to OpenShift, exactly the same. You bring your license to it. And that SVVP means that Microsoft provide 100% support over the operating system behavior as if it is an operating system, because at the end of the day, it is an operating system. It is a virtual machine. Does that make sense? Any other questions or feedback? I'll say I'm personally impressed at the speed, even of nested virt. I've used nested virt in the past, especially on things like OpenStack, and it's painfully slow. And this is actually usable. These are not big machines this is running on either. One of the major problems I've had, and I deal directly with the engineering team on this, is that you do need a lot of disk space. And the reason for that is you can overcommit disk space when you're writing containers because of the nature of the sharing of the file layers, and it sort of preempts. So you say, I've got a 20 gig disk and you can only be using 2 gigabit. When you're using a virtual machine, because of the nature of the virtual machine and the way the virtual machine works, it has to have access to the full file space. So, what the problems I found in the past with this is that I created 3 Fedora virtual machines and 2 Windows virtual machines, and I blew the disk. When the disk blows, you get disk pressure, and when you get disk pressure on a node, the node is unschedulable. And that's when you start to see problems, when the virtual machine can't schedule itself, or the CSI pods for the overt count schedule themselves. Does that make sense? I'll say the slides are going to be available, and I will make this recording available as well. If anyone wants any more information on CNV, feel free to contact me directly. So other questions come in. Yes, we have. The reason I'm a bit this is aimed at Alan. The reason I'm a bit reticent to say about it is that we do have some reference cases for OpenShift virtualization, but because OpenShift virtualization is so new, those reference cases are still sort of in the kick the tires stage. But we do have a major bank that is presently moving all of its virtualization estate directly to OpenShift virtualization, and that includes a lot of high performance compute, specifically high performance compute. I can't say which bank it is, but as soon as that is available, that's a public reference, we can make that available for people. And hopefully, because it's a public reference, we can do reference calls with them as well, if people are up for that. I mentioned requirement for storage when running non-local PVCs. That's related to required performance. Yeah, absolutely. We've got another additional product called. Sorry, I've got my brain's just shut down. OpenShift Container Storage, OCS, which is based on Ceph. Ceph is a very, very useful technology for doing this kind of virtualization PVCs because of the way it stores local content. So you can get some very, very fast performance if you're using OCS for this kind of things. But to be honest, any PVCs that gives you good performance across multiple nodes will give you good virtual machine performance. Because remember, when you're doing a virtual machines anyway with things like VMware or things like Rev, you've got distributed storage. So, and when a container is running, it's running locally. What do I expect the reference to be open to the public? I'd probably say two to 3 months. The reason for that, again, is that this is brand new technology. You know, OpenShift virtualization only really dropped as GA as part of the product at 4.6, and we've got some massive enhancements coming. And so what we're doing is we're working hand in hand with this customer to bring them the enhancements directly as part of the 4.7 and 4.8 releases, and the 2.6 plus releases of OpenShift virtualization. So yeah, I would say 2 months, but just ping off me and I'll pass information to you. Will it be possible to utilize a mission control for VMs? Yes, absolutely. Because the VMs themselves are exposed as PVCs, you could do scanning on those. We do have a lot of alerting and metrics capabilities that we can link into the virtual machines. There is some discussion I've seen on the engineering lists and forthcoming about being able to spool direct metrics and logs from the virtual machines themselves into things like Prometheus and Fluentd, but that's in hand. But yes, it should be possible to utilize the mission controls. Any more questions? Also, if you think of something after the fact, or when you're scanning the slides at a later date, when you're reading them to put yourself to sleep at night, and you come across something, feel free to drop me an email. I'm more than happy to demo this again to anyone who wants to see it and play with it. It is reasonably easy to install. The key thing with it is that run it on bare metal. Set up a cluster on some bare metal nodes, do a base installation of 4.6, install the operator as described in the slides, and away you go. Hopefully in the short term, we'll have some templates that allow you to kick off those containers I told you about, the container-based VMs. So it'll be things like base installations of Fedora, CentOS, potentially RHEL, RHEL 8, UBI, things like that. But unless anyone's got any other questions, I will stop recording and call it a day. And thank you for attending.